Hi, I'm Uwe, and I'm from an advisory board, and I have the great pleasure to introduce our next keynote speaker. Basically, our next speaker does not need any introduction. He's very well known for his great, entertaining talks, always very insightful, and offering new perspectives on seemingly well-known topics, and always served with a pinch of very fine humor. So please welcome on stage Kevlin Henney.
Hi, thank you very much for that kind introduction, Uwe. So, I'm honored to be introduced by you. So, what we're going to do, the next 45 minutes, we're going to go beyond the known knowns. In fact, as Uwe mentioned, this whole idea, one of the things I enjoy doing, and I don't just enjoy doing it, is sometimes look at things that we think are familiar and known and come back to them and realize that everything is a lot deeper than we expected. And sometimes the obvious is not as obvious, or we've been overlooking something. And often we overlook things because as human beings, we are always operating with incomplete knowledge. We cannot know everything. That's just a fundamental. We should always remember that as our opening position. We cannot know everything. So this idea of being able to organize our knowledge, I want to talk about that and its relationship to architecture, the what and the how things are built, and importantly, the relationship over time. We often think of architecture as it's very naturally a spatial metaphor, but I think we need to appreciate the time dimension a little more deeply and the relationship that we have with knowledge. So let's start off with, this is what I look like when I'm standing up. You can get in touch with me at a number of places if you'd like to follow up on anything. And if you can't remember this, that's fine. My parents gave me a very convenient internet unique name. And what have I been doing during the pandemic? Well, during the pandemic, I finished this book with Trisha G, 97 Things Every Programmer Should Know. I'd say probably about half of the advice in there goes beyond or is language independent, and goes beyond the kind of core aspects of language. Kind of the origin story of that is I did this about 10 years ago, 97 Things Every Programmer Should Know. I care very much about the detail and what that can reveal to us. But there's the bigger picture. So here I am talking at the Software Architecture Gathering. What qualifies me to be a software architecture speaker? Well, I have published 2 books with the word software architecture in the title. Let's just say that that's good enough, okay? Patterns. Now, there's a lot of misunderstandings about patterns. I'm not going to talk about that today. But I want to talk about one of the things that I found fascinating about patterns is that when properly understood, patterns are a process of inquiry. They are not a solution mechanism. Patterns are a process of inquiry. They are a process of discovery. They are a process of reasoning. They are a process of organizing our knowledge to clarify what we do and do not know. And if anything has helped me approach any software development problem, whatever scale, that is probably that. It's this idea that understanding that we know stuff, understanding that we don't know stuff, and understanding how to connect and organize stuff is fundamental. And indeed, we can see that this view is foreshadowed by the great Grace Hopper. And she said, "To me, programming is more than an important practical art. It is also a gigantic undertaking in the foundations of knowledge." Wow, does this not sound grand? This is fantastic. In one sense, what we're doing when you are building a system, the architecture is a means of organizing knowledge. You are not merely putting bits together. It is not simply a passive structure. It is an organization of knowledge that is executable. That is a very deep approach. So next time, if somebody says, I don't know if anybody still has business cards, I haven't had a business card for many years, but should you find the need to have a business card, then you want a job title there, or perhaps your LinkedIn profile, applied philosopher. Okay, that's what we do in software. It's applied philosophy. We take the stuff of thought and reasoning and knowledge, and we question it, we interrogate it, we structure it, we make it run. And we find out what doesn't run, and we find out where our assumptions are. And that's what I want to talk about today. But there is also something else. We often walk around with this idea that we can have complete knowledge. Indeed, there's a contrasting view put forward by the late Douglas Adams in The Hitchhiker's Guide to the Galaxy. Two philosophers there actually say, we demand rigidly defined areas of doubt and uncertainty. They are concerned that if everybody discovers the answer to life, the universe, and everything, that actually they will be out of a job. The whole job of a philosopher is to fill the space that is doubt and uncertainty. So they demand lines of demarcation. But it's okay. We're not just demanding this. Even if we didn't demand it, it turns out the universe is going to give us this. We cannot have complete knowledge. And we find this, the earlier part of last century was hugely disruptive for everything. The main program of physics and maths was hugely disrupted. There was this idea that we could know everything, that the universe was a clockwork universe. And then into this, we had quantum mechanics. This is Heisenberg's uncertainty principle, or one phrasing of Heisenberg's uncertainty principle. It turns out that if you know more of one thing, the position of something, you know a little bit less of it. It's momentum. If you know more of the momentum, then you know less of the position. It turns out that you cannot know these with the same fidelity. This is not fully knowable. We also find boundaries to what is visible, even in the scope of, say, general relativity, the other great theory of the earlier part of the last century. This is a picture of M87. The black hole event horizon telescope took this picture over a period of many months, and the final image was published, probably one of the iconic images of this century. And this is, we are looking at the shadow of a black hole. Beyond that event horizon, there's a lot we don't know. There's a boundary to what is knowable. We have challenges about what happens to information. But even away from the physics, even the pure idea of mathematics, the idea that mathematics could be complete and consistent was one of the great programs outlined by David Hilbert in 1900. 23 things he said, we must succeed in doing this. Turns out there's a whole bunch of stuff we can't do. And it turns out that Kurt Gödel in 1931 kind of demonstrated the boundaries of what is knowable, the boundaries that there can be statements that are true but are not decidedly true. And that undermined our idea that there's stuff that we just cannot know and cannot demonstrate. Now, you might say, okay, yeah, nice. Okay, we've talked the physics, we've talked the maths. What's that got to do with me? I'm in software development. I deal with business solutions and stuff like that. Yeah, of course you do. Right. So you deal with networks, right? So most things are delivered over networks. So my publisher, as in O'Reilly, there we go, book plug. A couple of years ago, there were some fires. Well, actually, every year there's fires in California, but this one was particularly significant, as was posted. Fire in California, can't read your ebook in Pennsylvania. This satisfies, is a beautiful illustration of Leslie Lamport's definition of a distributed system. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. There is a point here. These limits on knowability actually manifest themselves in very practical senses in distributed systems, as well as concurrent systems and so on. But distributed is kind of one of the most obvious things. And out of this, we have things like Brewer's theorem, also known as the CAP theorem, that was basically, it's coined in the latter part of the 1990s, but was demonstrated to be a theorem in the early 2000s. And that is very much to do with exactly what I've described here, is this idea that there is a boundary on what is knowable and what you can claim or state about a system. You can have consistency, you can have availability, you can have partition tolerance. Well, actually, no, you can't. You can have any two of those three. Okay? You cannot have all three. Partition tolerance basically means resilience to partial failure of a network. You can't have all three of those properties. Then they're the Heisenberg's uncertainty principle of distributed systems. There are boundaries to what we can know. But even without those boundaries, these are all out there in the world. I want to start in here. And Nassim Taleb, who's perhaps better known for this is his first book, Fooled by Randomness, and then there was The Black Swan, and then Anti-Fragility. And a lot of people in the Agile community are perhaps more familiar with the Anti-Fragile. And if you can get over his kind of like writing style, there's some really good stuff in this, and there's some important observations, and just a very simple one. Ultimately, when you are dealing with a software architecture, you are dealing with people. No matter how technical you are, no matter how technically you're approaching it, this is a people thing ultimately. I mean, think of it from another point of view. What is an architecture? An architecture in the real world is a place in which you live and work. It is a space of living and working. Therefore, architecture is ultimately for people. It defines the spaces and connections between the spaces that allow them to live, to do their job, to succeed in a particular, or to improve and be effective in a particular role. That is not at all different in software. The architecture is not merely there to deliver a set of capabilities in service form to clients. By which I mean software-based clients. It is there to deliver capabilities in terms of pricing to clients in the human sense, but also to the people who live within the architecture, the developers, the architects, and all the other technical roles that we find there. But importantly, we have this, again, boundary. But the boundary is now within us. People overvalue their knowledge and underestimate the probability of their being wrong. You know, when somebody tells you, they say, oh, yeah, we're going to need this feature. And you're looking at it and you're going like, well, you know, I don't think you will. Oh, no, we're pretty sure we'll need it. We think it's very important. And we're looking at something that's way down the backlog. And you can tell that they haven't really thought it through. I mean, you can't just come back and say, you know what? You have no idea what you're talking about. Because that's quite insulting. People aren't going to respond well to that. Even if it's true. Product owners don't know what they're talking about. Because they haven't built the product yet. They have an idea. There's no shortage of ideas, but they're confusing their ideas with what exists in the future. They don't know what exists in future. They think they know what they want, but the minute the future starts arriving, it will take a different course. But also, we are very safe in the knowledge that we believe we already have, and we hold on to that. The number of times I've had this with people, and this is not a software thing, where somebody will say, you kind of point something out, maybe it's about language or the use of a word or a technique, say a technique in maths or a technique in science or a technique or a historical fact or something like that. The number of times people come back and say, oh, but I was taught in school, as if school is the only source of truth. No, that piece of information was given to you by another human being in a time gone by. The probability that you recalled it perfectly is not high, but more importantly, the probability that it was given to you correctly is also not that high. In other words, question those things that you think are comfortable knowledge, because they're only comfortable because they're first. They are low in sedimentation. We need to recalibrate our understanding of what we do and don't know. Now, fortunately, we actually have a very convenient model. Philip Armour in 2000, which I now horrifyingly realize is 21 years ago, came up with the 5 orders of ignorance. 5 orders of ignorance were, he published it in Communications of the ACM. If you Google this, I think you can find copies. I think the reason I haven't put a URL on this is because I can't remember if those copies are actually appropriate or not, or if they are actually at the Communications of the ACM site. 5 orders of ignorance, and like a good modern developer, he counts from 0. 0, lack of ignorance. You know what you know. 1, lack of knowledge. You know what you don't know. There's a whole bunch of things I know I don't know. I don't know how to speak Japanese. I don't actually know how to prove Gödel's incompleteness theorems. I know that I don't know these things, and I'm comfortable with that. Now it gets interesting. Lack of awareness. I don't know that I don't know certain things, and they will often come as a surprise. Now, funnily enough, we're now moving into the bit that starts characterizing software development. Although I talked about this as being an organization of knowledge, the very process of what we do pushes us into this, and importantly, 3, lack of process. We don't know how to find out what we don't know. That's an interesting one. And then meta-ignorance. Well, I have some good news for you. Meta-ignorance is basically you don't know the 5 orders of ignorance. We have solved this problem. We have now reduced 5 to 4. Perfect. So let's reframe this in terms that actually people may find more comfortable, and which also gives us the title of this talk, Beyond the Known Knowns. The known knowns, the things you know that you know. The known unknowns, the things that are unknown, but you know that you don't know them, and you know that you don't know them. And then there's the unknown unknowns. Okay, this quote made famous by Donald Rumsfeld, possibly his only useful contribution to the course of human history. And then the unknowable unknowns. These things cannot be known, particularly if they are time dependent. They cannot be known until they are known. There's no other way you could find out. Until they reveal themselves, there is no other way you can find out. So let's have a look at these. The known knowns. This is our comfort zone, but already we should be cautious. Do not assume that everything that you know is actually true knowledge. Maybe it's just belief. There is a wonderful quote often attributed to Socrates. I know that I know nothing. But as I put there, possibly, maybe it wasn't him. You know, this is a long time ago. We're not very good at this stuff. We're not entirely sure that he said this, but it's often been attributed. We should start from a position of humility. An architect that goes in based on their knowledge. And of course, you want to use your knowledge. In fact, that's the whole point of my interest in patterns originally, was this idea of organizing and offering knowledge. It's about knowledge sharing. It's about communicating beyond the code and saying, and this is why. Okay, the whole pattern concept has informed many other ideas and influenced many other ideas. We see this in domain-driven design. We see this in architecture decision records. This idea of a way of reasoning and breaking down your knowledge and offering it to people. Because when you present your knowledge, people will then say, that's not quite what we meant. They will clarify. But also, if you do think you know everything, that's probably a bigger problem. And that is an interesting one, because many development approaches, historically, people have based development on trying to maximize. And many people, I certainly get it now, where they say, oh, yes, when we're doing the architecture phase, there's no architecture phase? What is this? There's a bit in the life cycle which we do architecture, which suggests we don't do architecture after that or before that. And that's a very strange thing. But it also suggests that we can have complete maximal knowledge, that we can know everything that we need to know in this period. That is remarkably unfortunate, because it turns out the universe is not going to cooperate with us on this one. So we need to open with a position, no matter what your experience, you can have decades of experience. Approach it as if you did know nothing. Okay, use the beginner's mind. You will find out more about the new technologies, the old technologies, the domain, organizational structures. If you go in with the assumption that you're a beginner, you will see more than if you go in with the assumption that you already know the stuff. Yeah, it's just one of those, there's almost a paradox here. So let's move on to where it starts getting interesting. The known unknowns. Sometimes we know that we don't know something. Hey, we're going to use this framework. We can use this middleware. Oh yeah, we're going to use a NoSQL database. We haven't used it before, but we know that. That's fine. But there's a problem here. No, this is a good thing, but there is a problem here. Is we still overestimate our ability to know what we don't know. The interesting thing is we downgrade the importance or the significance of it. This was captured rather nicely in the Planning Fallacy. The winner of the Nobel, the economics Nobel, Daniel Kahneman, and his late colleague, Amos Tversky, talked about the planning fallacy. It's a cognitive bias. And these days, cognitive biases, we are much more aware of them. They're all the rage. We have a much deeper knowledge of them. But back when this was proposed in the 1970s, this was still relatively novel. They define this phenomenon as the tendency to underestimate the amount of time needed to complete a future task, due in part to the reliance on overly optimistic performance scenarios. In other words, even when you don't know something, you will still be optimistic about it. And there's a very simple reason. This is a little bit like, let's imagine that the known knowns, I mean, I'm putting them into 0 and 1 categories. It's probably a little more shades of gray. There are fractions here. But I want you to think that the known knowns are the things that are immediately around you that you can see. They're visible to you. As you go towards the horizon, there are things there you can't properly see, but you know that they're there. This is the known unknowns. okay? But they're in the distance and they're not very big, and so they're not very important to you. And this is the curious thing. There's a kind of a self-serving feedback cycle in our head that basically says that the things that you know are important and worth knowing. Why? Because you know them. Because you know them. The things that you don't know, that you recognize that you don't know, are less important than the things that you know. Well, why are they less important? Well, because if they were important, you'd know them, right? In other words, you're using your knowledge as a ranking mechanism of their importance. The presence of knowledge becomes a ranking mechanism. So we have this bias. Now, you got to recognize that this is built into us. You get, with every human, you get a whole bunch of cognitive biases free. And I did a talk. When was it? 8 years ago, OOP in Munich, and it was on cognitive biases. And one guy came up to me afterwards and he said, "How do I fix this?" And it's just like, you don't think you understand the point of the talk. The point is you can't fix it. That's part of what it is to be human. But we can certainly compensate for it. And one of those is by doubting a little and being cautious, but also looking at things that don't work. And none of this knowledge is new. I'm going to take you back in time to 1968, the famous NATO Software Engineering Conference in Garmisch. And many people sort of think, oh, software engineering, yeah, they coined the term. They didn't. It was Margaret Hamilton. She coined the term. And they think, oh, software engineering, that's where all this kind of, idea of plan-driven development came from and, all the rest of it. And it's just like, no, actually, they recognized there were limits then. This is not news. Okay, we've been spending, every generation rediscovers this for themselves or ignores it at their peril. The most deadly thing in software is the concept, which almost universally seems to be followed. And he was saying this in the late 1960s, as if we'd been doing software development for ages. Software development had been only really going since the 1950s. And they already see the problems. What we've done the last 50 years, honestly, I don't know what we have done the last 50 years. I mean, honestly, our hardware's got a lot better, which has dragged the software along with it. But, we could do better. You're going to specify what you're going to do and then do it. And that is where most of our troubles come from. This was already known. This is not news. So that architecting phase, that design phase, let's also look back at 1968. The design process is an iterative one. Whoa, okay. So again, process-wise, what have we spent the last half century doing? Catching up with ourselves. And indeed, we can go back to the 1950s. And here's a nice water wheel. Where did I take a picture of this? When I used to be able to travel. This was Switzerland. And there's a very simple model that is very helpful when we are dealing with things that we don't know, things where we don't know completely. We have knowledge of the things we don't have knowledge about, but there's also the question of the next category we'll get to. Don't just plan it and do it. Don't do all the plan, then all the do. And plan is interesting because plan as a word, it suggests there are two sides to plan. One side to planning is an arrangement in time. Another side of plan is it's an arrangement in space. I think both are relevant when we talk about software. Okay. So study, reflect on this, and then act on what you've learned and repeat. It is a cycle, as is our acquisition of knowledge. The cycle of acquiring knowledge in regular English, everyday English, has a different name. We call it learning. Okay. But if knowledge acquisition cycle sounds cooler, go for it. It obviously looks better on a slide, especially if you're presenting to other people in your organization. Knowledge acquisition cycle. Honestly, it's called learning. Learning is a process of revision and repetition and accumulation. And it's a lot messier than iterative development in that sense. I'm not going to claim it is iterative. It doesn't have bounded time boxes and clear goals. But I want to say that there is something more about the acquisition of knowledge that we can learn from ourselves in terms of learning. Now, occasionally you'll see people call this PDCA rather than PDSA, Plan, Do, Study, Act. Sometimes people call it Plan, Do, Check, Act, PDCA. I don't really like that term. That's not really the original formalism. Deming and Shewhart originally formulated this. Shewhart, I think, formulated first, then Deming, and he preferred the term study. Check sounds very quick and cursory. The word study sounds slow, and I think that's very helpful to us because everybody's trying to do things faster these days. That turns out not to be the trick. You don't want to deliver software faster. I keep seeing this everywhere. People talk about deliver faster. the distinction that I have come across in recent years that is more valuable is you want to deliver sooner. That does not necessarily mean you have to travel faster. Faster sounds exhausting for a very simple reason. It is. What we need to do is slow down and look at what we actually know and what we don't know. Our goal is to arrive sooner. So let us exercise our knowledge. And perhaps adjust. This is something that Demings was more keener on later in his life. Adjust is a better way of looking at it than act. And the point here is this is how we're going to deal with the things that we don't yet know. Rather than making assumptions, and rather than being surprised, we are going to treat everything as a hypothesis, a work in progress. Your architecture is a hypothesis. It is not a static entity. What you are saying is, given what we know, given our knowledge of the tools, given the way that our team works, given our relationship with our client, given our understanding of the existing code base, and so on and so on, our hypothesis is that we believe this is the right architecture that we can develop in the next few sprints. And then you test your hypothesis. You run an experiment. Obviously, the language of experiment is not the language that many people, like product owners, want to hear, but it is an experiment. You're testing your hypothesis. And if that hypothesis turns out to be problematic, then you adjust. And the whole point here is it doesn't matter how much intellectual side. It turns out that applied philosophy, it's a practical philosophy. It's not theoretical. It's not just in your head. You have to finish things. That's what you learn from. You learn by finishing things. Okay, as the author Neil Gaiman highlighted. So even when we're dealing with the things that we know we don't know, it turns out that there are many surprises, but not as many surprises as they are with the unknown unknowns. The things we didn't know, we didn't know. Now, it turns out there are many kinds of unknown unknowns. Let me just present you with a rather nice example that illustrates one of the categories of unknown unknowns. This is the Ariane 5 launcher, which at the time, Ariane 6 is superseding it. Actually, I can't remember what the capabilities are, but Ariane 5 at the time was one of the world's most powerful launchers. These days, it is one of the launchers that has the most reliable track record. Okay, what you're looking at is an image June 1996, so 25 years ago. This is the 4th of June, 1996. It's been mounted for launch. It is launching. This is probably 1 or 2 seconds into flight. This is a little bit after 38 seconds into flight. It turns out to have been one of the world's most expensive fireworks. And why did it go boom? This was its maiden launch. So in other words, I've said it's one of the world's most reliable launchers, one of the most reliable launch systems, yet it had a really bad start in life. Why? It was a software bug. And we actually know exactly what the causes of this bug are. Here is the code. It is Ada code. I won't, this is not a code review talk. There are things to be said about it. And what is missing here is you can see the if statements. The if statements are doing what is known as clamping. These days, if you're using a capable language, then you will have typically a method or function called clamp, where you are basically trying to threshold. You have a value and you're trying to make sure that it does. Here's a value. I need to make sure that it's no larger than this and no lower than that. So therefore, if it's larger, put it there. If it's lower, put it there. Okay, you're clamping it between two values. That's what all those if statements for. But if you're an Ada programmer, you like writing if. You like typing lots. And you like writing in a kind of pseudo Fortran style. This used to be known as Adatran, this style. Now, what you may notice is that the line with all the red is not surrounded by a clamping if, else if. And the reason it's not surrounded by that is because there is no way that this conversion, there's a type conversion here, there is no way that this conversion from a 16-bit from a 64-bit, I know it says 32, but all this stuff says 32, it's actually 64-bit. 64-bit floating point number to a 16-bit signed integer. There is no way that this conversion can fail. So therefore, there's no need to clamp it. And the whole point about this is that this is a velocity conversion. And in Ariane 4, there is no way that you can exceed this, given the rocket's design. It's physically not possible. Now, if you are listening carefully, and I haven't sent you to sleep yet, if you are listening carefully, you'll have noticed I just said Ariane 4. Yes, folks, this is code reuse in action. Just so you know what code reuse looks like, this is code reuse, okay? This is what you're seeing here on the screen. This is code reuse, because what we've just done is we've gone and reused something from Ariane 4 in Ariane 5, which is a physically different launcher, and in which it is quite possible to exceed this. By the way, this is also dead code, which they forgot to remove. So there's a kind of like a perfect storm of an assumption that is no longer valid for the platform, but because the code is not going to be used, the capability is not tested. We have just fallen into the shadow of the unknown unknowns. This is, most unknown unknowns are, the most familiar category is bugs. They are things that we did not know we did not know. It's just like if somebody asks you, hey, how long is it going to take you to fix the bugs on that platform? Which platform? The one you're going to develop next year. But we haven't developed it yet. How can I know how long it's going to take to fix the bugs? That is an unknown unknown. We don't have enough information. Yeah. A bug is not simply a negative feature. I desperately worry when people try and prioritize defect work alongside feature work, as if a defect is like a negative user story. That's a terrible metaphor. I mean, it's cute at one level, but leave it, because it does not require the same knowledge. When I tell you what I want, then even if I'm not clear about it, I have a vision about what I'm expecting. When we have something we don't even know why it's there, if somebody says, why do you want this feature? And I give them a business case, or I say, I can justify it. Nobody's going to come to me and say, why do you want this bug? That bug, we didn't put it there for a reason. We lack the knowledge about the knowledge that it embodies. In other words, we're dealing in many cases with assumptions. And assumptions are kind of interesting because assumptions are invisible. I've paralleled them here with this idea that from a point of view, philosophically, epistemologically, the philosophy of knowledge, if you've ever had the experience of stepping on a piece of Lego barefoot, you'll be familiar with what I'm talking about. But what I'm saying here is that, if you like, you're walking into a dark room, barefoot, and I've told you there are Lego bricks on the floor. There are assumptions. The problem is, even when you know you have assumptions, you won't know what they are until you've stepped on them. Assumptions are a very curious piece of knowledge, because we don't know that we have that knowledge until it's contradicted. Yeah. If somebody says, please list all of your assumptions, I've even seen project documents with, list of assumptions. That's just actually not possible within the realms of philosophy. You cannot list your assumptions. The best you can ever do is list of known assumptions so far, because most of your assumptions are not known, and they will not be known until you run into them, until you step on them and contradict them. The moment, maybe you're saying something, and you're showing some code, you're outlining an approach, and your colleague says, actually, it's not quite like that, it's like this. And you go, oh, I had assumed that. At that moment, you discovered you'd had this knowledge all of the time. So you only discover, you mostly discover your assumptions by contradiction. They're a very curious piece of knowledge. And this broad idea, when we talk about the structural perspective of architecture, David Parnas back in 1971 made this kind of key observation. These days we talk a lot about dependency management, and we have a lot of tools for dependencies, and that's great. But those are, he talked more broadly. These dependencies, the dependencies you need to look at are not just the ones that are obvious in the code, where one piece of code uses another piece of code. I can see that. I can use tools to make that visible. I can use my eyes to make that visible. I can use reviews to make that visible. I can look at the build system and I can see that. It's real. Okay, that dependency is there. This service calls this service. This launches this. I can see all of this stuff. But there's a deeper idea. It's not just that I can see it. There's another set of dependencies, connections. The connections between modules are the assumptions which the modules make about each other. There's a whole class of dependencies that do not have this obvious A uses B syntax, but they're still there. There are certain assumptions. Oh, I had assumed that the threading model, in other words, I've got a piece of code and it works until you put it in a particular threading context. What was my assumption? This will only be accessed in a single threaded way. Yeah, okay, that was a very simple assumption. Why would anybody want to do anything else? And now I suddenly discover somebody had made a different assumption, a collision of assumptions. We have assumed that we're using a particular, I was assuming you were sending me JSON. No, well, turns out that actually we've decided to extend JSON a bit. Oh, it's JSON-like, but not JSON. Okay, that's unfortunate. There's all kinds of things. We discover these on collision, on contradiction. So when we start looking at what we actually know, so imagine, here's the world of our knowledge, or rather the world of our system. And here is the part of the system we're working on, and that's where our focus is. And when somebody says, show me the dependencies in your code base, then you draw something like this. But it's all the code that you own. I mean, either you personally or somebody else within your organizational reach owns it. And you have a kind of a simple view. These are the connections. This is what my dependency management tool shows. The problem is the dependency world is bigger because all of these things use other things. These days we build on very, very full stacks indeed. I mean, I find it slightly ironic that, I get a lot, so we find a lot of people, they say, I'm a full stack developer. And they work on a tiny, tiny piece of the technology stack. They don't work on device drivers. They don't work on middleware. They're using somebody else's code and they're saying, I'm full stack. You're not full stack. You're a teeny weeny squinchy bit of the stack. Typically, full stack development means I use JavaScript and I put things on a screen and I talk to a database. That's a hugely small, that's a very, very narrow piece of the stack. So our vocabulary invites us to think small. Whereas we actually need to think, all that stuff I depend on, I need to say that's part of my dependency set. Sometimes when I say, what are your dependencies? Somebody will list off this. Oh, okay, so what are you using? And then they'll start saying the programming language and other tools and things like that. And that's the important thing. The platform is part of your assumption set as well. And a lot of people say, oh, yeah, that's not really part of our dependencies. Really? If I got rid of that operating system tomorrow, would your system still run? If I got rid of those compilers, if I decommission that language, would you still have a system? Turns out that it's like the air. It's everywhere. We breathe it. We forget we actually depend on it. It's like gravity. I don't wake up every morning and think, well, I hope gravity's reliable today. I hope that oxygen doesn't run out. I happen to live, very fortunately, in a world in which that is available. But it's so pervasive that we don't even see it as important. I have so many people who say, oh, the programming language is not part of my architecture. Yeah, yeah, that's very sweet. You need to go and talk to some big companies and find out what they've learned over the years. Your programming language, your code, your operating system choices, these are woven into the fabric of what you have built so intimately you can't even see it. It's transparent like the air. And then there's the market. You depend on the market. Because honestly, if the market didn't exist, why would you be writing the software? Okay. The requirements, governance. People often ask, where does governance and regulation fit? Are those, and people say, those are user requirements. No, they're not user requirements at all. They are market requirements. They are governance requirements. The user doesn't have to tell you, by the way, please respect the market and the rules of the game. Those are woven into the fabric of where you're working. That's product requirements, but they don't come from the user. They are in the space in which you're working. If you take that away, then it changes your architecture. But the way we normally look at architecture from a point of view of knowledge is like this. It's just like our knowledge is collapsed in. And when I've spoken to people saying, oh, you need to expand your view of your architecture, they ended up with a very small view and say, oh, well, no, those aren't part of my architecture, really. If I pull that dependency, will it still work? And then we have unmanaged technical debt. It's an even smaller world. So there's some really interesting things here about actually what we can and cannot see within our architecture, how we view this. And we have this very simple idea of, I haven't actually defined architecture yet, so I guess I ought to. Martin Fowler said it's a term lots of people try to define with little agreement. These days, we're probably closer to agreement. There are two common elements. One is the highest level breakdown of a system into its parts, in other words, the big block diagram, and the other decisions that are hard to change. I don't find the idea that my architecture is a box diagram very useful. That's a view of the architecture, but that is not the architecture. Okay, there's a very important distinction there. A view is not the whole. Based on that theme, Grady Booch has this observation: all architecture is design, but not all design is architecture. It's a subset relationship. Architecture is the decisions that are significant, that shape the system, and we define that significance by cost of change. Now, the problem is, until you change something, you don't necessarily know what the cost of change is. You see, there's a paradox here. Now, of course, we can get some clues. You know, there's if we're going to talk about architecture as a metaphor, this is a very fine book. Christmas is Coming: How Buildings Learn. It's actually about architecture and about buildings, and it shows us how buildings evolve over time. It also, and how they respond. And from this, there's this wonderful diagram that is used in the big ball of mud paper that is about the idea that a functional building can be understood in terms of its different layers, particularly office buildings, layers of change. And you should organize your system in terms of the layers of change and the rate of change, and appreciate it from that point of view. And in the big ball of mud paper, they have a pattern, shearing layers. The idea of the observation here that the things in different layers change at different speeds. Therefore, structure your system around the different speeds. Now, why does that matter when it comes to trying to predict the future? Well, as observed in the which book have I got? I've got a pile of books on my desk. Christmas has come early. There we go. Your Code is a Crime Scene by Adam Tornell. Code analytics. Measuring change frequencies is based on the idea that code that has changed in the past is likely to change again. So we can't predict the future, but one of the benefits of a legacy system is that we can see the past. And we should use that as input into our decisions. We should use that to highlight the changes and the uncertainties that we have. And you know, there's a number of different techniques that we can explore for structuring our time and for dealing with things that we are not sure about. Again, another book which I think is often overlooked. People talk about lean development a lot these days, but they rarely go back to the source. Mary and Tom Poppendick in 2003 published this. They talked about a number of techniques before lean became popular, and their way of they structured their vocabulary was very, very interesting. They talked about a lot about concurrent development, but they talked about delaying commitment. Delay commitment until the last responsible moment. That is a moment at which failing to make a decision eliminates important alternatives. You can't know everything in advance. The past will tell you something, but then sometimes we see other options. Do we commit now? No, we don't know. We don't have enough knowledge yet to know which option is appropriate. And this also relates to the idea of real options from Olaf Marson and Chris Matz, which can be simply understood in terms of three aspects. There are three properties that options have. Options have value, options expire, never commit early unless you know why. So when you have options, make sure that you keep them open. Architecture is filled with options. So the last category, the unknowable unknowns. Architecture is the decisions you wish you could get right early in a project, but you are not necessarily more likely to get them right than any other. Ralph Johnson, Gang of Four. It's a lovely way of looking at this, that even if you did know, you're not guaranteed that that's going to make a difference or the difference you hope. You're going to miss something else. As Randy Sharp observed, if you don't end up regretting your early technology decisions, you're probably over-engineered. In other words, you probably wasted a lot of time doing things that were unnecessary, rather than saying, we built our software in order to be changed. If we are also successful, yes, and we're going to plan in the fact that success will trigger further change. Our hypothesis will evolve. The problem is that people often do over-design. Okay, science fiction author William Gibson noted that which is over-designed, too highly specific, anticipates outcome. The anticipation guarantees, if not failure, the absence of grace. We will be clumsy and it will be painful and expensive. The thing we need to recognize is that when we're dealing with the unknowable unknowns, it's about the future. And what I love about this is that we don't even know who said this. I mean, people think it's Niels Bohr, but this was just last century. And we're not even sure this is true. So how good are, for all I've said about the past, even the past is opaque to us. We know more about the past than the future, but damn, we don't know as much about the past as we think we do. And then we get this kind of like classic habits that people have. We're going to have a roadmap, and you can go on to Google and just Google PowerPoint templates for product roadmaps, and it'll give you pages and pages of stuff like this. And they're all very pretty. They look like a road. They show you all the kind of standard things. There's only one problem. Now, let me show you a roadmap. Let me actually show you a real roadmap. This is where I live. I live in Bristol. I want you to notice the difference between these two. It turns out that when people show you a roadmap, they only show you one road, as if the future was certain and that there's only a well-defined set of posts. Anybody who shows you a roadmap with one road, and maybe you've done this, always kind of raise your hand and say, where are the other roads? Because a roadmap is not useful unless you have the other roads. The whole point is navigation. Our ability to predict the future is terrible. I mean, let's just look at this one. This is, as I said, you can find loads of these online. I want to just point out 2020. Who here had global pandemic that basically wipes out our everyday business and restructures the way that we have to approach business and jeopardizes the very structure of our business? I don't think anybody had that in their roadmaps, because this is unknowable. We do not have a process for finding out what we do not know until it happens. How does that affect us? Well, it affects us because, here's an example. Many people talk about, oh, let's prioritize our requirements by business value. Okay, you've got a backlog of requirements. Let's prioritize by business value. I have some very bad news for you. You can't do that. I mean, I'm not saying this, so don't misunderstand me. I'm not saying you shouldn't do that. I'm saying you can't. I'm saying this is the stuff that we talked about at the beginning of the talk. It's against the laws of physics to be able to prioritize by business value. Yeah, you need to be able to go backwards in time. You need to go to the future and then go backwards again. You can't prioritize by business value because you don't know what the business value is. How can you prioritize by a thing that you don't know? The best you can do is prioritize by estimated business value, but don't confuse the two ideas. Estimated is not actual. I mean, how many times do we have to tell people your estimate is not actually what happens? It is a belief that needs to be validated, but it could be completely wrong. So never use the phrase prioritize by business value. Always use the phrase prioritize by estimated business value, because unless you have a time machine, you cannot do this. It is against the physics that we understand of the universe. And honestly, if you do have a time machine, why are you sitting here watching my talk? There's much more interesting things to do. Go and see the dinosaurs. So there is a point here that we have got to, if we appreciate the nature and the shape of development, then another book on building architecture gives us a kind of a better understanding of how we should think about our design. That there's an experience that we have. Properly gaining control of the design process tends to feel like one is losing control of the design process. We are no longer offering knowledge and certainty. What we're actually offering is meta strategies. We're saying, here are the things that we know, and we will build on those. Here are the things that we don't know, and we will work through those to clarify that our assumptions are true. But also, by building what we are planning to do, rather than just thinking about it, we engage in what Dan Terhos North calls deliberate discovery. We put ourselves in the situation where if there is something to be discovered, the probability goes up. If you are going to discover those assumptions, if you are going to discover those Lego bricks, you're not going to discover them by standing there and not walking on them. You've got to walk on them tentatively, carefully, do things that cause other things to happen, do things that cause the knowledge to come towards you, but then also have the humility to understand that there will be things that utterly surprise you, and that your plan at that point is to let go of the plan. So thank you very much. Now, I believe we have time for questions. I've already seen I've got a couple of questions in the queue. Yes. How does the knowledge... Yes.
Hi.
How does the knowledge acquisition cycle... Oh, I can read that. Yeah, sorry, I can see it in the chat as well. So how does the knowledge acquisition cycle correspond to the OODA loop? Good question. Boyd's OODA loop. So you observe, you orient yourself, you decide, and then you act. PDSA is a little bit, it's kind of like the OODA loop, but turned through, it starts in a different position. Rather than the PDSA cycle, so for me, it's a phase difference. And this is actually a question that was raised originally when I was doing a workshop a number of years ago with John Jagger. And we both put different slides in. I put the PDSA slide in, he put the OODA loop slide in. It's just like, oh, and it's just like, what's the relationship between these? And then we worked out if we change the names of the things, actually, it turns out they start in a different position. And the idea of observe and orient is actually closer to study and act. We start in a different position. We are taking a situation that exists rather than designing a situation. Here is what we think we're going to do. Let's see how that worked out. We start from a different position. We start with what shall we do? Let us look around and study. So yeah, it's a really good question, because what it does is it shows that a lot of these loops map onto each other, but sometimes slightly different. They start in a different position, and it's suitable from a kind of different point of view. So yeah, that's really good.
Great. Let's go on to the next one.
Right. When the water wheel turned counterclockwise, other than the knowledge. Oh, you know what? You're probably right. It's just maybe I need to flip the image. Yeah. I used it figuratively, but I will go back and check. And if it is indeed that, I will do a reverse. So I'm quite happy to be corrected on that. That's an assumption, because that water wheel is actually static. It's never going anywhere. But in truth, yeah, that's a good point. So yeah, I'm always happy. By the way, the best way, if you ever want people to give you feedback on your slides, the best way to do it is to do your presentation. You'll always find the bugs that people can't find when you're looking at them yourself. So thank you very much for that. Okay, so what methods or tools do you use to gain more insight, to expand knowledge? Right. So honestly, there's a lot of different things. The simplest one is so never treat it as one source. In other words, let me quote Émile Auguste Chartier on this one. One of my favorite quotes: "There is nothing more dangerous than an idea when you have only one idea." So if somebody comes up and says, "I have the tool that is going to solve whatever it is," be very suspicious. You need more ideas. So the first thing is approach this as a broad-based problem. You need to have multiple strategies. That's similar to that idea of losing control of the design process. You don't have one way. You're dealing with a situation that has incomplete knowledge. So you better have more than one trick. How do I know if this is going to be the right thing? Okay, simplest thing, build some of it. That's the first thing. Actually put that thing into code. Stop with the meetings, actually get some of it into code. But we don't know what we're doing. Exactly. It's software. It's soft. You get to change it, except when you don't. And that's the problem, is a lot of our software has lost its softness. We don't pay enough attention to that. We haven't been looking after it very well. And it loses its softness. So therefore, that brings about fear. But also, we are also frightened in another sense of creating small things that we throw away. Because a lot of people say, well, we need to be delivering functionality all the time. Absolutely, you do not need to be delivering functionality all the time. You need to figure out what it is that you need to deliver all the time. In fact, I find one of the most frustrating things is that these days, the great idea of continuous integration, continuous deployment, the continuous everything, is that I am getting loads of updates to applications that I use that is just like, stop doing the updates. Just sit down for a moment and figure out what is it that you're trying to do, rather than just messing the users up. Take a moment, think, rest. Figure out if there's an easier way to do this rather than upsetting everybody all of the time. We have continuous annoyance these days. So the real trick is you want to continue, and anybody who's telling you, oh, you need to continuously deliver value. No, you don't. That's nonsense. Value is an ill-defined term. Unless you're prepared to define it, it doesn't mean anything. So continuously delivering value to the customer is a nice high-level statement. That's great. But we're supposed to deal with the stuff that's real. Not just what do you mean by value, but what is the knowledge that is going to allow us to create something and keep on creating it? That's the key thing. So therefore, you need to build what you're talking about. You need to build prototypes. Guess what? They don't deliver value to a customer. They deliver value to the development organization for some definition of value. You need to, if you can't deliver as much as you'd hoped, and so therefore people are being sprint driven, which is exhausting. They're expected to have increments of functionality. Sometimes the real trick is to take a step back and go, we don't yet know enough to deliver this. So therefore, what we need to do is develop something that's going to show us what we need to develop. You need to take a little bit of time out there, and it needs to be done continuously. So this is there's an ebb and a flow. You're constantly looking at this. So building, talking to people. Guess what? The really hard part of talking to people is listening to people. Look for where those uncertainties are. Ask those questions. Have review sessions. Slow down. Remember I said PDSA, S is for study. Why do I like the word study rather than check? Because study sounds slow. Because it's supposed to slow you down so you can pay attention. If you just check it, you move on. You're all about the speed. But I just said it's not about the fast. It's not about the speed. What you need to do is pause and observe. Look for knowledge wherever it comes. Look for knowledge in strange places. In other words, the code base can tell you things. Look at the patterns in the code base. That's why I mentioned the Adam Thornhill book, because there it's amazing how much information we ignore, and therefore how much knowledge we neglect to get. If you have an existing code base that is filled with knowledge, I don't just mean you've got a bunch of classes and you've got a bunch of methods and I mean that you can see patterns of change. Remember I said architecture, we need to think of it not just as structural and spatial, we need to think of it as a time-based thing. What is it that keeps changing? What are the things that don't keep changing, and why don't they keep changing? Maybe that piece of code is incredibly stable because it's really good and we've never needed to change it. Maybe that piece of code is incredibly stable because it's dead. Maybe that piece of code is incredibly stable because it's so bad that nobody dares go near it. The point there is that metrics don't give you an answer, they give you better questions. So if you start reframing architecture as an activity, an ongoing activity that is a process of inquiry and is going to involve other people and the artifacts and looking at the things you already have from a slightly different point of view, that would be the way I'd think that. So it's a very broad-based approach.
Great. Thank you. So we are running short on time. There are a few more questions. I would love to invite you to go into Hopin and answer those in text if you have any spare time. One big question that I've seen come up is, are the slides already published somewhere, or is there a place that they can look at your slide content?
They are not already published, because I never publish my slides these days until I've actually delivered them, because who knows what I'm going to say when I say it. I haven't put them anywhere, and I don't know. That's a very good question. I don't know.
We can absolutely put them with the recording.
Perfect. In which case, that is the answer to that question. I will send those slides through.
Great.
Okay,
well,
thank you very
much. We'll
much.
look forward to getting that from you, and we'll get your slides published with the recording after the conference.
Cool.
Kevlin, I want to thank you again for joining us, and I wish you a wonderful rest of the day.
And you. Thank you very much.
Thank you. Take care.